Hi, we're going to consider the following density function, where f of x is 1/4 for 0 to 4, and it's 0 otherwise. Let's visualize this distribution. So on the x-axis, here's going to be 4, and I'll color the distribution here in red. So I'm going to put this f to be in red, and let's use a nicer pen than that. And this value is 1/4. Okay, so it goes from 0 to 4 here, and otherwise is going to be 0. So from that value on, it's 0, and from this value on is going to be 0. So the only way that we have any probability here is for x between 0 and 4. Okay, kind of intuitive looking at this. So let's calculate the probability that x is bigger than 3. Well, if we look at this, this will be 0, that's 1, here's going to be 2, here's going to be 3. We've chosen a nice number, and if we think of probability here as the number of outcomes that x can occur for x bigger than 3, divided by the total probability, well, this here, this is 1/4 of the area, because there's a total of 4 boxes that fit here. So if we count these boxes, right, here's going to be 1, there's going to be 2, there's going to be 3, here's 4. 4 equal boxes. So I might say, this is 1/4. But here's another way to look at this. In the situation in which we don't have equal boxes, which can occur. Hey, the area of this box right here to this entire region, and might have to just try and make things a little bit nicer there, to this entire region here, so the shaded to the entire region, this is given by the integral from 3 to 4 of f of x dx. And that is equal to the integral from 3 to 4 of f of x is just 1/4 dx. So this will be 1/4 x from 4 to 3, which is 1/4 times 4 minus 1/4, 4 times by 3, which is 1/4. So in general, if we have a function whose probability is not nicely symmetrical like this, then we can still calculate probability. So if we want to do calculations of probability, we have this rule. Probability x is between a and b is given by the integral from a to b of f of x dx. And one thing that I notice is, hey, it doesn't matter if I include less than or equal to or not there. It's still the same probability. So i.e., probability of a point is 0. Now, it also follows, my apologies, didn't mean to write that in red. It also follows that if I want to calculate probability x is less than b, this will be the integral from minus infinity to b of f of x dx. And you might say, hey, if I integrate from minus infinity, how's that possible? Well, remember, everything to the left of 0 here has 0 probability, so you're really just integrating from 0 to b. Okay. Now here's the second one, probability x is bigger than a. This will be the integral from a to infinity of f of x dx. And the final thing that I notice is I said probability of a point is 0, and that's because this corresponds to the probability x is less than or equal to a and bigger than or equal to a. And the area of a point is 0. And that's just given by this calculation. So it doesn't matter if I put less than or equal to on any of these. It's the same way that we calculate probability for a continuous distribution. There are, of course, some caveats to this that are not covered in this class. Okay, so for us, probability of point 0, if you want to get into the theoretical definitions of probability, you need to take more probability theory. One thing you might have said is, hey, in this calculation, I took 1 out of 4, the 1 being the one equal box to the 4 other equal boxes. Why don't I divide by the total area? Well, if we did that, I just want to note the total area here would be, in this example, it's 0 to 4 of f of x dx, integral from 0 to 4 of 1/4 dx, that's equal to x over 4, 0 to 4, and that will be 4 out of 4 minus 0 out of 4, which is 1. So there's a requirement to be a valid density function. And they are as follows. So the first one, there are two requirements. It's that total probability is 1. But total probability is just given by this integral. And this is what you'll see most commonly. Okay. The second requirement is as follows. Only positive probability. And this is equivalent to the following. So i.e. p of x is greater than or equal to 0. So this requirement and this requirement are the two requirements you need to check if you're asked if you have a valid probability density function. So let's just go through an example here. And before I go through this example, I just want to say a few words about a context in which you might have this density function. So this density function might arise, for example, in the callback time of when you call someone and you call a call center and they say, would you like a call back? And they say, you can either choose to be called back in the morning from 8 to 12 or from 12 to 4. And you were to ask, well, do you think someone would come more likely in the first hour or the last hour? And they respond, all time intervals are equally likely. And here I also need to say that time intervals of equal length. Okay. So if you've ever had a scenario where they say, no, you need to be available for the whole time, there's no time that's more likely to occur than another time, you have a uniform distribution. Here the callback time is continuous. The random variable is time. We can have minutes, seconds, etc. So it's on an interval level of measurement. The random variable x can have any number of decimals as opposed to a discrete distribution where it's just 1, 2, 3 successes, something like that. Okay, so let's consider this example here. F of x is going to be k over x, and here x has to be bigger than or equal to 1 and less than e squared, and this is 0 else. So my first question is to determine the value of k that makes f of x a valid density function. Okay, well, we have the requirements up here. So one is that total probability needs to be equal to 1. So that is, I need to integrate from minus infinity to infinity of f of x dx. So you're like, wow, that's an improper integral. How am I going to do this? But then you look at the density function. It's only non-zero from 1 to e squared. So I only need to actually integrate from 1 to e squared of k over x dx. Okay, I remember the antiderivative of this is k times the natural logarithm of x from 1 to e squared. So this is going to be k times this ln of e squared minus k times the ln of 1. Hey, the natural logarithm of e squared, that's 2. So that's 2 times k. The natural logarithm 1 is 0. So what's the value of k? 1 is equal to 2k is what this question says, and k is equal to 1/2. Okay, so f of x is going to be equal to 1 over 2x from 1, excuse me, got a little carried away there, 1 to e squared, and 0 else. Okay, well, the second thing I would notice is that when x is bigger than 1, f of x is bigger than or equal to 0. And if it's not bigger than or equal to, if it's not between 1 and e squared, where it's positive, then it's 0. So we meet both criteria 1 and 2 here. Total probability is 1, only positive probability. So f of x is a valid density function. Okay. Just one other question here is, let's just try calculating a probability with this, because, um, you know, I think if I was to graph this density function, it's not going to be nice and symmetrical, right? This density function is 1 over 2x from 1 to e squared. And I think it's going to look something like that. A kind of a strictly monotonic decreasing function, okay? And otherwise it's 0. So what if I want to calculate the probability that that x is between 1 and 2? I'm going to have some sort of area here, and that corresponds to probability. So let's calculate probability x is less than 2. Well, we were told how to do that earlier. Calculation of probability, the red part is optional. And I'm going to calculate that this is minus infinity to 2 of f of x dx. But remember, it's only non-zero probability for x being at least 1. So I wind up with the integral from 1 to 2 of 1 over 2x dx. And this will be equal to 1/2 times this ln of x from 1 to 2, which is be 1/2 times the ln of 2 minus 1/2 times this ln of 1. And we need to do the ln of 1 and recall that that is 0, and so we're just left with ln of 2 over 2. And I think that's approximately 0.34. Okay. So just a little bit of an introduction here. One thing that I'd like to point out, introduction to calculations of probability and requirements of a continuous probability density function. I'd like to point out that that is a continuous interval. X can take any number of values between 1 and e squared. In fact, an infinite number. Here as well, that interval has an infinite number of outcomes. Okay, thank you very much.